Okay, so let's get started. I changed the title slightly. Hopefully it'll be clear in a second. So just as a jumping off point, so if there's more references and things, so we have like a workshop series, and this Fast ML 2023 this year, last month in London. You can go there. There's a lot of these talks are there in a lot more detail. I'm just trying to give you a flavor of everything that's going on. And then yesterday, all the talks are up now, I think. So yesterday we had our first edition of the SML ICCAD, and it was really great. It was actually great to see other people from other communities coming in and asking questions too. It was really great. So in terms of like other good places to start. So we have the Fast Machine Learning web page, and then also like Shushi said, the A3D3 pages as well. So the NSF Institute, which is really providing a good community for us, or it's a nexus for the Fast ML activities. And then actually, as a part of the second version of this workshop, we wrote a white paper, which kind of lays out the vision of how, we really need all of these different communities to come together to do really cool science. All right, so first, it's great to see everybody in person. I've known a lot of you online in the past. Actually, the last time I gave a virtual talk to this crowd or some version of this crowd, it was literally the day that Xilinx became AMD. And I was really confused with what to say during the talk. It was Valentine's Day. Do you remember this? Valentine's Day of last year. I was like, oh no, what if I say the wrong thing? Like, should I? Because I had all these Xilinx references in my slides, and I was like, did I switch them all to AMD the day before? I was like, I forget it. Okay. Okay, so the structure of the talk is just like this. So we'll talk about kind of like the vision on the science side. And then the second half will be kind of then how that translates into, all the fun sort of ML, co-design, hardware research that's going on. I'm going to focus really on the embedded systems more so than the coprocessor, just because the story is already very large. But a lot of the same discussions apply as well. All right. So the first part is just actually it's an evolution of how this community, which kind of is well, it's a really new thing, is expanding, and kind of how we imagine this can fit into the larger world. All right, so this all started with the Large Hadron Collider. This is an experiment which a number of us work on. This is at CERN in Switzerland, 100 meters underground, 17 miles of, I should keep the same units, 26 kilometers circumference. Collisions at this experiment, 10 billion collisions a second, 10 petabytes of data per second, right? So a lot of data, right? And this is what comes out, right? So we need all of that, that big accelerator to make really high energy collisions, and then we can look at really massive objects, right? All right, so why? So why do we do this? So we have, a lot of it is kind of trying to understand a lot of those early questions about the universe, fundamental questions about nature. And the higher collisions, the more you can explore what happened earlier and earlier in the universe, right? So you can see different accelerators and how they map onto, where we are in the history of the universe. Now we're at a billionth of a second after the Big Bang, recreating that in the lab and trying to understand what's going on. And so we try to answer questions, about, fundamental physics. I always like to say it's at the most basic level, it's the stuff and how that stuff talks to each other, right? So at the particle level. So and we call them interactions and forces, right? And there are lots of fundamental questions. These are a couple of my favorites. Why are we here? So there's matter, there's antimatter, but there's some asymmetry that happened in the very early universe. And that's why there's more matter than antimatter. And so we're all here. Another really big question is, what is dark matter? We know that, there's 5 times more dark matter than regular matter. Dark matter is not antimatter, by the way, they're different things.
So just one quick question. Do we know that for sure that there is more matter than antimatter, or could it be that antimatter is somewhere else in the universe and we don't see it?
I guess that's a good question. What do you guys think? I would say It's possible. I
Would
guess,
there be
eventually.
an annihilation at the edge if there was a antimatter area?
I guess if there was a part of the universe which is predominantly antimatter and there was no matter, but then,
So it's unlikely, but you can't exclude that possibility.
Yeah, that's right.
yeah.
That's a very good question. And it's been a big debate in physics world. But I want to follow the idea that if there's another world predominated by antimatter, there must be a boundary between matter and antimatter. And if this happens, then you see a huge annihilation happening in that age.
Yeah.
Mm.
So if we look at the sky, whether we see some area provide a huge light source,
Mhm.
this could be a support for the idea we have another world with antimatter dominant.
But we don't see that right now.
We haven't seen yet. Yeah, we haven't seen it, but the universe is weird, so.
We have like models that aren't favored but are possible.
Mm.
Yeah.
Thank you.
Okay, cool. Good. So how do we study these questions? So everyone always shows this like giant picture, the ring, and it's huge, and that's how we get a lot of energy. But people also don't always talk about that we need a lot of those collisions, right? Why do we need 10 billion collisions a second, right? It's because here's the let's say the probability of okay, in units that don't matter, but like the probability of an interaction, and then the probability of some particular process that we care about, right? This is already a billion times lower, and then we're looking for maybe new physics, which may be denser. So something that is happening every billion of billions of collisions, right? So that's why we're looking for really rare things, and we need to be able to have lots of collisions to go sort through all that data, right? And so this is the experiment. It's a CMS. Here's a person down here, and it's like 5 stories tall. And the experiment has something like 1 billion detector channels. It takes a picture every 40 million times a second, and so you get lots of data, right? This is where the 10 petabytes for something of data.
40
comes from.
million in a second.
Every 25 nanosecond, that's like a heartbeat, right? And so we have this very complicated data reduction path before we even look at the data. So you can do things like on detector ASIC compression. This is already like 10 times the average internet traffic in North America. We go to an FPGA filter stack. Then we pass this on to like an off-the-shelf CPU, GPU farm. And then after that, then we store things sort of at the 5 kilohertz rate. It's already exabytes of data in the end, and then we ship that all around the world and we do analysis, right? So you have all these different sort of compute problems at different scales. I'm going to focus mostly on this side of the picture. This is the embedded system side for the talk. But there's a lot of activity and interest also in sort of accelerator, compute acceleration, sort of on the right side of the picture as well. Okay, so just in really quick in sort of just an overview of the architecture of the filter farm. It's like, if we've ever counted, have you ever got? It's like hundreds of FPGAs, right? And each of these tiny little boxes is an FPGA, right? The boards look like this. This is one example of one of the boards. It's got a giant heat sink on it. It's got like 100 and something, 25 gig links on it. So it's processing a lot of data, and we have hundreds of these things. And they're all taking data from different parts of the detector and trying to combine it in different ways. And you can see if you can find something interesting. And this is a fly from Shoni, which is kind of showing how people are already exploring how you can put machine learning algorithms into these different FPGAs so that you can do a better job of taking the detector hits, turning them into higher level objects, and then deciding if we need to keep the event or not, right? So that's kind of the flow of how it goes. And just so there's a lot of FPGA programming going on in this project. There's, I would say, hundreds of physicists working on this, and this is like each of these different subsystems. Like these are some of the flow plans that we're thinking about these different projects. There's a lot of A lot of PG engineering going on with lots of these are just random acronyms for some of these subsystems, but there's a lot going on. How do you put all these algorithms together? This is actually a really good one. This is the thing at the end, and it has lots of little algorithms deciding. You can see everyone has like a little block. They're trying to decide, can I keep my physics or not my physics?
Question here. So the job of this cluster is to just filter, prune what's relevant, what's not relevant before you broadcast it to the world.
Exactly, yeah. There's a second stage, but yes. So you have this 40 million collisions every second. And then we use this filter farm to knock it down to maybe sort of hundreds of kilohertz. So at some point you take the sort of coarse data, you read enough PDs and you decide, is this interesting or not? So it's like a filter, but on the number of events basically. And that gets passed to a farm of CPUs and GPUs.
Yeah,
Okay.
so like that point is like we keep the entire event. There's other mechanisms where we can just like make the events smaller, so like save less data, but physicists are notoriously very protective over the raw data. So we want like the normal path is to keep the raw data, all the raw data for a given event.
So yeah, so you see this, so that like you have all 40, so I should have got this more detail. You have 40 million going this way, and then after you make a decision and you decide of these 40 million, let's keep 100,000 or so, thousands, and then this gets passed on. So this is kind of like a control loop, which is keep or don't keep.
And do you change the particles that hit each other, or is it always the same thing that go?
It's always 2 protons. Well, okay,
Always 2 protons.
to 90th percent, and sometimes later they put in other heavy ions, but yeah, usually it's protons.
Mostly proton. Right?
Yeah. But they make protons are bags of other particles, right? Of quarks, right? And so those particles, they can make all of these different processes, right? So you can.
Another silly question.
Yeah.
Where do you store this data? This much data?
Yeah. So we don't. So here it's not stored, right? The storage only happens at this stage.
Okay.
Right. So that's why now you're down by several orders of magnitude, and you're not at petabytes per second, you're gigabytes per second.
And it's actually stored somewhere. You keep all this data.
Yeah. And this is literally true that there are sites all over the world that keep parts of the data. It's a very coordinated effort.
And you're trying to maximize the energetic, energy of the proton together, so that you maximize the energy of each collision, or is it?
So the energy, okay, so the first order is fixed. So it's fixed by the size of the ring. So what we're trying to do is, okay, so the whole reason for building the machine is to get as much energy as possible, right? But then once you have that, you need to get as many collisions as possible. Okay, you want to study all of as many as you can.
So there's two objectives, right? Reaching the highest possible energy, and then having the most possible number of connections per second, so that you can generate.
Yeah, and you can find sort of some of these strange interactions that happen very rarely, right? Or something.
And every few years there is an update of this collision, and you get it. You are able to increase the energy.
So yeah, so the energy is actually a big part of the field discussion. The discussion in the field now is what the next colliders, but these are now very big projects, or 20, 30-year projects to get more energy, because it's a lot of very costly, right, to build something that's like this. And so then the next one will have to be, twice the energy and be like twice as big.
We're planning the 100, right?
Yeah, they're planning a 100-kilometer one. That'll go like
in this area.
yes, yeah. It'll go under the lake. Yeah, so there's a big sort of global discussion going on about what that next energy is. But the upgrades that we're doing now are more like, upgrading some of the detector systems so that you can read out faster, you can read out more granular and things like that.
It's more incremental right now. But
right.
At some point you need to, once you have maximized all the incremental improvement, then you have to move to the next bigger
energy, right, exactly. Or yeah. Okay, yeah, maybe I won't go to the.
Yeah, I have a quick question, Nhan.
Sure, yeah.
Yeah, so it looks like one of the thing that you would like the FPGA to have here is a very high bandwidth consumption capability.
Definitely. These boards are running at 25 gigs, 100 links. They are, those links are full. Yeah.
Okay.
And we have a few microseconds to make the decisions, right? That's also written on the slide. You have about 12 microseconds for the data to get through the entire system. So multiple FPGA hops as well.
Nice, got it, thanks.
Okay, so I'll just give a couple of examples in detail. So like here's a design where you were looking for a muon, but a muon that didn't come right from the middle of the detector, but maybe a little bit further away. And so there's a neural network that's, trying to find out if that, do that and this is a very complex environment. And so like with the neural network, you can cut the data rate by a factor of 2, something like that. There's also, I'll talk about this at the end, there's new ideas on doing like anomaly detection, just looking for strange things in the detector. And then, like I said, there's all this kind of active exploration. And like that's going on basically in this slide here. All this is kind of understanding what's needed for the next generation system. I'll also say that I didn't talk about it all, but on detector, there's also data compression, and we also are looking into ASICs. Sujit is one of the people that really love this project on putting the neural networks inside of the ASIC on the front end to do data compression, and then that gets sent to FPGAs. Right? So at every stage of the stack, it's really valuable to put AI techniques throughout the system. Okay, so that's the LHC. And actually, I saw this slide from Shani at the level 1 workshop, and I was like, oh, they're quoting this is the white paper at the beginning. So I'll just read it. The scientific discoveries come from groundbreaking ideas and the capability to validate those ideas by testing nature at new scales, right? So finer and more precise temporal and spatial resolution, right? So that's what we're talking about, trying to get higher energy and then look at the exclusions with more and more resolution, right? And so we get an explosion of data, and ML is a really powerful approach. So to fully unleash the power of machine learning and accelerate discoveries, it's necessary to embed it into our scientific processes, our instruments, and our detectors. So that's kind of the vision for the community in general. I think it's a nice way to put it. So I'm going to do something kind of now, take a step back and be something like very generic, right? Like if you're doing any experiment, right? You have some sensor, right? And then you get some analog signals, right? Some particles going through this. You get some pulse or some spectra, right? Or something like that. Then you have to digitize it. Then you have to reduce the data. And then you save it to disk, right? Whether you're doing this in the university lab with a microscope or you're doing this at the scale with a large hadron collider. And if you just do the numbers, right? If you take one channel, it's 10 bits. Now you want to take a picture 1 million times a second, not even 40 million. And then now you have 100,000 channels, right? Now you're getting data rates which are already quite unmanageable, so terabits per second, right? And so this is the idea, is that at each stage, this is too much data, too late, right? So this is why we need to embed intelligence at every stage of the experimentation. And it's something that not many fields are equipped to do. And LHC is one of them, and we've been working on this problem for a long time, but some fields are just starting this process, right? So that's kind of like where the sort of trickle-down effect from these technologies is making its way into different areas of science. So let me give a completely different example. I'm not a fusion expert, so don't ask me too much about fusion, but this is a project that we started about a year ago, and actually because some people came to the last FastML workshop that were in fusion and interested in this topic, right? So obviously this would be a great thing. It's getting a lot of attention in the news, right? There was this study about doing reinforcement learning for controlling plasmas. And even recently there was this like net energy gain from fusion, even just down the street at Livermore. And so how can we use some of the technologies that we developed, say for Large Hadron Collider in this environment? So we were able to work with some people at Columbia. They have a sort of a tokamak in their basement. It's good for doing a test. It's like a test tokamak for developing lots of techniques. And then you look at kind of the things that they worry about in the timescales, right? So like one of the hardest problems that they have is a thing called magnetohydrodynamics. It's instabilities that come, right? So then you can't contain the plasma anymore, right? And that's what you need for lasting sustained fusion reactions. But the timescales on which those MHD instabilities happen, right, is at the order of microseconds. Okay. And so, the question is, can we have a control loop that's able to operate on the order of, let's say, hundreds of kilohertz or megahertz to be able to keep these these plasmas sort of stable. So we started, and there's links all over the talk. I'll share the slides at some point, and you can find more details there. So one thing that we were working on with them is actually putting a high-speed camera. There's like a little window in the tokamak, and you can take a video of the plasma. And this is a new way of monitoring this. They usually put like magnetic sensors inside of the plasma, but then the problem is that when it gets too hot, you get damaged really easily. So this is like a non-invasive way of monitoring what's going on in the plasma. And I think so this is one of our collaborators put this video together, which is really cool, right? So this is sort of how the plasma changes over time. But if you look at the time steps, right, this is basically in microseconds, right? So we're looking at this over maybe a fraction of a millisecond. This is how fast things are changing in there, right? And so the question is, can we, do some CNN on this, understand what's going on in the plasma, and then make some correction to keep the plasma stable on this time scale, right? And I'll say that we just presented this at a fusion workshop last week, or a collaboration in Columbia, and I was sitting and I don't know anything about fusion, and the people were like, I wish I could have control at like the millisecond scale, and so I'm like, oh, we can do this at the microsecond scale, right? So it's really new capabilities for that field, right? Okay, so here's the dream. We have an open source high-speed camera off-the-shelf stack that you can build, right? You get a high-speed camera. You can buy from it's a Phantom camera company. This is a board. It's got a Xilinx FPGA or AMD's FPGA on it from Eurosys. And they have this nice setup where you can actually just drop designs in there. So we can drop CNN in there and do some work for this application. So that's what we show. Here's a model that we've developed. Here's the dotted lines of linear regression and SVD algorithms. This is what you're trying to do is you're trying to predict the amplitude of the plasma field, and doing it high resolution is always better. So first of all, the machine learning technique is better than sort of linear regression techniques. It's much tighter, and then we have to optimize the model. So this is like the full Keras model, and then we're doing quantization, we're training, we're doing pruning, then we're optimizing the model. And you still get pretty good results in blue, but this is the one we want to implement on the FPGA. It's a small FPGA, actually, by the way. Most of these companies that are building scientific instrumentation with FPGAs on it, they don't use the big honking ones. They use the smaller ones, right? So we had to fit it in quite a small area. And then we did hyperparameter optimization. So one of the students, Ryan, he was going through tuning reuse factor and finding how we could fit this within a few microsecond latency and on this board, right? Okay, and so this is the prototype system. Here's this high-speed camera, and here is actually a very sort of detailed timing diagram about everything that's happening here, right? And then we're capturing all of this information on this oscilloscope and making sure that we're doing all the inferences, right? So you do an exposure, you get the frame, then you have to send it to the readout board, and then the neural network takes about 7 microseconds. And you do this over and over again, right, to try and have a feedback loop for this plasma. And then we pipeline this, right? So you can do, as you're doing the inference, you can do another frame. So we're getting about 120 kiloframes per second. And like I said, this is, for that field, probably I don't think they knew that this was even possible, right? So, and the whole point is to make it accessible for them too. They're not, FPGA experts, right? How do you say, here, just start with this model and we'll be able to implement it into a system for you. All right, so that's the vision. And so I like to show this plot a lot now. This is kind of all different types of applications for different sciences. We're working a lot now on trying to develop benchmark tasks so that people working on very different problems can see how they're all related to each other. So benchmarks bring innovation, but having grand challenges really gets people excited, right? Fusion, oh, that would be cool, but I don't know how to start. Right? We'll start with this one task on magnetohydrodynamics stability or something like that. So that's the vision. That's what we're hoping to get to. I'll give a few more examples. So like One here, there was a talk at last year's FSML about people using, again, the same technologies to do real-time seizure detection, right? That would be cool. All of the beam lines and stuff there, right, that need to be to provide particles to these experiments, right? This is miles and miles of accelerator, right? There are hundreds of thousands of monitoring devices, lots of daily alarms. How do you operate this large but complex, right? To be able to provide this quality of beam to different experiments. And then this goes all the way down to like, this is the collaboration we have, and Josh has a talk on this, right? Every university lab has a fancy microscope, right? And this is what they're doing, right? They're shooting low energy electrons through some material, looking at the diffraction patterns. All right, but now they want to do this at megahertz scale, right? With 100,000 pixels in their detector, right? So, and then we talked about multi-messenger astronomy. This is something that we do at Fermilab. So understanding, can we see neutrinos from supernova bursts in the galaxy, right? So very different scales, but not different problems, right? From the computing and data reduction point of view. Here's the multi-messenger astronomy one. This is a plot from Michael Cowan that she showed yesterday. So you have neutrinos, but you have gravitational waves, you have photons from telescopes. All of these things can be used together to understand what's going on in the cosmos. There were a couple of talks yesterday about quantum readout, qubits, quantum computing, right? So in the end, given the decorrelation times of qubits, right, you have to do readout and control at the time scale microseconds to milliseconds. Right? This is an RF socket board, that's reading out data from superconducting qubits, right? So, right, and then finally, this is a talk that Giuseppe gave yesterday. This is the hardest problem we have on the benchmarks right now. This is 40 million collisions a second, trying to read out on the sensor exactly, and do data reduction there, not even passing it off. So like in the silicon, right? So you have two layers, they're bump bonded. You have the sensor, you have the readout chip, and you're doing analog and digital on the same chip. And so we have a first prototype here. So these are the analog islands digitizing the signals, and then the neural network in the red kind of embedded throughout the rest of the silicon, right? So, all of these different problems, and seemingly unrelated, but a lot of the technologies are actually quite similar. And so bringing that to bear on these problems, which are much harder than Internet of Things or mobile devices, I think can really spur innovation. All right. Okay, so that's the end of the first part. I'll stop for a second. Any questions?
So that's the reason I stopped reading books.
And it's actually fun for me as a particle physicist to understand some of these other problems, right? Like I don't know anything about fusion, but it'd be cool if we could help out with that. All right, so now we'll go to the second part of the talk. This is this joke I've been working on for a few talk iterations now. Let's see how it goes. So it's a quadruple entendre. You know what double entendre is? It's just like double meaning. So it means four things in the context of this talk. So then everyone has to have a ChatGPT reference, right? So I asked ChatGPT, what is the edge of tomorrow? This is like 2 or version 2. So maybe it's much smarter now. So it's a movie. Has anyone seen the movie? No.
Yeah, of course.
Yes. If you haven't seen the movie, the way I explain it to people, it's like Groundhog's Day plus Independence Day, right?
No.
What do you mean?
No.
Yeah, it's like aliens come and they come every day. Okay, so so this is the obviously not what is meant by this, but it's actually not crazy. So I think probably a couple of years after we started doing this type of work, there was actually I came across this article. It's actually from CERN Courier from 1990, and the ideas are not. Oh, we had this talk from John Borchek from Berkeley yesterday, talking about I've been working on this since the 90s. It's actually in particle physics has been around. People have been thinking about this since the 90s, right? There's a VLSI neural network chip, this ETAN something from Intel, right? Where people were trying to do this type of work, right? And at Fermilab, at Slack, down the road. People have been thinking about this problem, especially for particle physics experiments. So I thought, are we just doomed to repeat history over and over again, and we're not going to make any real progress? So I was starting to think, well, what's really changed in the past 30 years or so? And so I will try and break it down into these 4 areas: necessity, hardware, research, and tools. So necessity, right? So obviously, everyone has their obligatory Moore's law plot, but I mean, it's true, right? I mean, at the time, there wasn't this societal need in the 90s that there is now with autonomous vehicles or industry or mobile phones, internet things, right? So I think and then even in the science side, right, all of these scientific experiments now also have the same problem, right? So now there's this growing need. That always helps, right? Obviously, the hardware has changed a ton. Even just from the 90s to now, it's more than 2 orders of magnitude in terms of feature size for transistors. So obviously, that's making computing power much more prevalent. And then the machine learning research side, right? Being able to implement all of these things, software, right? We talked about that yesterday. How do you abstract these algorithms down into hardware? The things like Vitis and so on. And then the tools are really important, right? So that, I think all of this combination of things has really made, I think this idea, edge computing really a lot more sort of accessible now. I'll say it that way. All right. Okay. You did not so well the first time. You're trying a second time, but I meant actually in the context of AI. What is the edge of tomorrow? And so the potential for AI to surpass human intelligence in the near future. And so this is a little bit worrying, but maybe we're starting to get there already with ChatGPT. Okay, but that's also not what I meant. So I said, what about in the case of edge sensing? So let's talk about that. Okay, and so this can be useful for applications where low latency or real-time processing is required, such as industrial automation, autonomous vehicles, and IoT. Good. So we're getting there. That's what we want to do. Edge sensing. It reduces the amount of data. I mean, good. Okay, so on the third time we got it. But then I asked, okay, well, are there any other contexts in which the edge of tomorrow makes sense? Let's see what it comes up with. It could also refer to the point at which a new scientific discovery or breakthrough is about to change the way we understand the world. Okay, so that's like the talk. So ChatGPT got it in four prompts. I did these in order. I didn't ask it 100 questions to get these. I did it. These are the 4 questions that I asked.
It's trying to answer your question the way you want it. It is like,
yeah, there's some prompt engineering going on.
It's like, you mean in this way, so I answer this way. I don't care about the answer itself as long as you're happy.
Yeah, that's right. Yeah. Okay. All right. So the rest of this talk will just be about a lot of the research directions. Efficient can mean a lot of things to a lot of people. I think efficient algorithms is really important, but if you don't have efficient tools, efficient hardware, efficient workflows, then it doesn't matter, right? And I think the goal in the end, at least this is my personal vision, is that we've done a lot on the edge computing side. There's still a lot of research to do there, but it touches on a lot of other areas of AI, right? So robustness, we heard a little bit about that yesterday. Autonomous systems, we're not there yet, right? There's a lot of things that are still done very manually, but that's where you want to get to, right? All right, so efficient code design. I think everyone here knows what HLS for ML is, but the main point is just that we have this code design process, and that gets us from the model to the hardware, and in the HLS for ML case, we've already been talking about it as the FPGA's flow, also the ASICs and so on. But there's a lot of collaborations that we've kind of have happened because we started with this, whether it's a QCares or Brevitas, QOnix, there's a lot of, this is a whole flow, right? And it's an ecosystem. All right, so first we'll talk about on the algorithm side. Okay, so the first one is, there's a ton of literature on sparse dequantization. There's still very active areas of research. Here's just the famous table from Horowitz talking about the different power numbers or different computations, and then of course coding as well, right? So I'll just say that even with amongst AMD and the fast machine learning community, there's been already a lot of work in this area. This is actually the first thing that we did with I guess at the time it was Xilinx Research. I guess now it's RAD, AMD RAD or something. And we started this looking at quantization aware pruning. More recently, this is another paper we just put out on Hessian aware QAT. And so, you have these big design space exploration and using Hessians to be able to choose optimal points for you without having to do, all the work of scanning every single bit width and every single accumulator size is something that is of course really interesting to everybody. And so I'll say, in the context of embedded and reconfigurable systems, there are a lot of open questions, especially how to take advantage of extremely customizable quantization, right? I'll talk a little bit later about, looking at exploring each bit of a neural network, right? In this way be 3, and that way be 4, and that way be 6 within the same layer, right? Is that even useful? We have a lot of discussions with you all also about building use-specific sparse compute engines. And I think getting to this area, right? How do, every time you make a choice, you get this exploding design space, right? And so how do we explore that design space efficiently? I think we're starting to see that now. We've got the tools to do, one efficient, let's say, synthesis of a model, and then now you have to do this loop, whatever, 10 to the 6 times, right? It becomes cumbersome. So how do you find the right design space, right point for your problem? That's the other thing about scientific applications; they're quite bespoke, right? You can get a camera that needs 100 kiloframes per second, and this one needs 1, and that one needs 40 million, right? And then the size of the models change a lot. So how do you get to design for your applications?
So just a quick question, because my naive question.
Yeah.
Hessian aware, are we talking second derivative?
Right, yeah, exactly. So looking at the second derivatives to decide which layers should be quantized with which values, basically, which precision.
Oh, interesting.
Hi, Nhan, just one quick question, just for the audience sake, maybe spend few minutes on HLS for ML tool, right? Like maybe people might not be aware of the tool, right? Like what was the motivation behind it and how it is, let's say, different from Fin and other frameworks out there?
Actually, that might be okay. I will. Yeah, that sounds great. I wasn't sure everyone's familiarity. I have a slide in 3 slides where we can talk about this in a little more detail.
Perfect. Perfect.
Yeah.
Sounds good.
Okay. So the ideas of quantization and sparsity, right? They're very generic techniques, and I think that's great. It's a good place to start. That there are other ideas that people are trying to think about, which where you can gain efficiency from using our knowledge, right, of the problem, right? So this goes usually by, in the words, distillation or inductive bias. And there was this cool talk by Ryan Liu at the workshop in London, where he talked about knowledge distillation, right? So you have a teacher model. This is a giant model. It knows about things like Lorentz equivariance, right? So how do you use the symmetries of the particle physics problem and embed it into your neural network? This is a very large model. How do you just embed that into an MLP? And will it learn anything, right? So this is another way to gain efficiency, right? And so this is a plot, showing, okay, so these are this is log scale, by the way, but showing that if you train the MLP from scratch, this is as well as you could do for this problem, and obviously this way is better, right? And depending on the amount of knowledge you try to distill into this MLP, you can actually do better on this particular task. And there's actually, you should go to the talk, there's a really interesting thing. It also learned about symmetries of the problem. So there's another plot in this talk which shows that if you then try and mess with the system by boosting it to a different rest frame, actually the MLP learns about the symmetries of the problem, even though it didn't know about it sort of a priori from scratch, right? So, but this is a way to get more performance through using your expert knowledge and more efficient architectures. There's also this paper that was on the archive. It's by people that we know, but don't work with them directly. This one is really cool. Okay, the title is obviously grabbing your attention. 19 parameters is all you need. And they took the same problem where people are putting hundreds of thousands of parameters in, and they did it in 19 and got state-of-the-art performance. I will say though that just be careful. So for a lot of these really high throughput applications, it's not memory that we're bounded by, but it's actually compute. And so they're doing lots of calculations in addition to that just don't have parameters. And so even though it's memory light is not necessarily computationally light, although this is something I'd like to talk with these folks about. Okay. So anyway, you have the quantization, you have the sparsity, and then you have other techniques that where you use knowledge from the problem and able to create even more efficient algorithms, and also hopefully robust as well. Okay. All right. Okay, so efficient tools for co-design. So Yaman gave a great talk at the workshop in London, talking about being able to build tools that can aid with the co-design process, right? And so QOnix is one of the projects that we worked on with them, sort of in collaboration, and being able to we had this problem where we weren't able to necessarily speak the same language about quantization, right? And so there's a lot of work to that. Custom Onyx ops for quantization, manipulating and verifying graphs, and models, right? And this is something that's co-maintained by AMD. Here's the point maybe where I'll stop. So maybe Abhishek, I guess what the tool flow for actually fin and HLS for ML is you start with the quantization. Well, you start with some training framework. Ideally, it's quantization aware. So these are 3 of them. You go into the QOnix originally started as a way for us to have interoperability between the tools. And then you can do HLS for ML and fin. In the end, they spit out HLS and then go into the design flow. There are many similarities. I think spiritually, their data flow, architectures, highly customizable, very low bit precisions. And then there are some key differences also in terms of like the range of quantizations that are available for the different tools, and also I think also the hardware that it supports. That's kind of what I'd say the biggest differences are. Do you want to ask more questions on that part, Abhishek?
I think I think that's sorted. Just trying so that people in the audience understands the HLS for ML motivation, right? Like why like it's for physics people, right? Like they don't want to deal with any Verilog and HLS, so for them it's modeled to hardware without any hardware design skills.
Right.
And yeah, just the differences between like why would someone want to use HLS for ML if fin is out there, right? Like those kind of questions.
Yeah, I think it's spiritually there's a really high a lot of alignment. I think we were talking about this last night, right? That for the different communities, right? There's a different barrier for entry, right? Like scientists who don't know much about hardware design or anything like that, we want to be able to maintain that ease of use, right? But still do expert. But this is the flow. I can probably talk for a while about the differences and the similarities, but I think at a high level they're quite similar. As and where they, I guess probably you all know kind of also the boundary between like Fin and Vitis AI and things like that, and so where particular use cases and applications are say better suited for each one, and I think that would probably be similar for HLS. But we do try and support other hardware as well, other companies who maybe shouldn't be named here, but different FPGA vendors and also ASIC. So that's one thing that's a bit different about the different tool types.
I think the fin question will come back in the afternoon.
Yeah.
Again.
Please do. I think it's easier as a back and forth for sure.
So you mentioned custom data types here, or custom bit widths. What kind of data types do you see like in your applications? Are there certain preferred integer formats, floating point formats?
They're weird, put it that way, right? I mean, it's basically what is the dynamic range of the things that I'm sensing, and make the bit widths that, right? So like Andrew, when you were Fermilab, you worked on this very weird custom float data type, right? That's in the like a 3, 4.
Like a piecewise linear encoding.
All right.
But it has to have a huge dynamic range and pretty good, pretty good quantization error. So that was how it got designed into the chip.
Do any of like the, I guess, industry standard like BFloat 16, do you use any of those ones, or it really has to be really customized for?
On the sensing level, I think it's extremely customized. I think like, yeah, BFloat 16 and this maybe more on the co-processing side. Things are already digitized. But even in the all FPGA system, kind of earlier, right? I mean, it's completely custom, right? We chose the energy to be 4 bits and then this position to be 3 bits, and then we pack it up. And it's based purely on the geometry of the detector.
Well, and then you have the encoder, right, which is an even different level of customization to
The econ.
reading. Yeah.
Yeah. We have an auto encoder, which also is, I'm trying to encode at the encoding layer state.
But you can actually specify that how much actually you use fixed point precision, for example. And you like the 90% is fixed point precision, 10% is float point.
Yeah. It's all, I would say, we actually had a discussion about this with Yaman at the SML workshop. Some people were thinking about wanting to support in QONIX some custom fixed floating point, but QONIX is currently, and so then HLS Fermilab and I guess Thin at the moment support floating point, right? Fixed point and integer.
Okay.
And and I would say like a lot of our applications are fixed point after that for initial sensing layer. So like, we have, all these custom data, integer representations of the data, and then like usually as soon as it goes into a network, we typically use fixed point or just like some standard kind of integer. But it can still vary by layer because again, we're just trying to like study the design space and make the model as small as possible.
Yeah, I don't say something wrong. Okay, and so actually out of this project, while QONIX was the main output, actually some of these other formats came out, which I think are being discussed internally here. I think people are thinking about how to use them, which is QCDQ, with quantized optical clipping. So it's kind of a deeper dive into this challenge, kind of sort of uncovered other possibilities. And then actually this is something that we were surprised at. This is the PyPy stats for QONIX, and it's like hundreds of downloads a day, and we're not actually sure who's downloading it and what they're using it for, but we think it's for like a lot of like the graph manipulation, but we don't know. And it jumped up, I think, somewhere right around the workshop as well. So you can take the average here and after the workshop, and it's grown again. I'm not really sure what they're using it for. Okay, cool. And then Vladimir gave this great talk yesterday on sort of the direction of HLS Fermilab. And we do have this balance, right? We have this balance between like what we have now, which is really configurable fixed architectures versus direct translation and really maximal flexibility. And how do we balance? This is kind of an interesting question. So, for me, like it is a delicate balance, right? Of ease of use for non-experts and having a really low barrier to entry, but also having optimal solutions and being able to incorporate state-of-the-art research, right? And so this is something we can talk about this afternoon too, is in terms of like vision for directions and how to implement this. Okay. Anything you want to add? Okay, all right, and so now on to hardware, efficient equipment for hardware. This is a slide I stole famously from you, Abhishek, on activities that we're actively discussing. There was this great work by one of Brian Kastner's students on so we work on this MLPerf tiny data set. And then after we had the models, the student went through and tried to then implement the solution, but using AI engines, and they did quite well. And we're talking about how to even improve that implementation as well. So hopefully this looks familiar to some of you. But this is another active area where we would like to kind of discuss more and figure out how to best us make progress and contribute. Okay, all right, and then I kind of want to say one philosophical thing about workflows and collaborations. Right, so I mean, one of the key features for FastML, I mean, that has made it such that you can just ask ChatGPT how to convert a neural network from Keras to HLS using HLS for ML, and it gives it to you in these 5 easy steps, right? And it's because it's open source. There's a lot of work around it, so it's community driven, but it's also user driven. You can find discussions on Stack Overflow that maybe no one else even knew about, things like that. And then it's accessible and usable. Again, it started with I would say with the customer base, so to speak. And from there, it's always had this vision of being accessible and usable for non-experts as a low barrier to entry. And of course, we had a lot of great collaborations with all of you, several papers, QOnix. I didn't talk about this very much, kind of just tangentially or peripherally, but we did a joint submission for ML for Tiny. It was the only FPGA submission. It was an open submission. Explorations of sparse blocks, AI engines, just lots of good conversations. And something I'm not talking about at all, but also maybe we'll talk about later in the afternoon, is also connection with the RF Stock and Pink team for this open source quantum instrumentation and control kit that's basically built off of RF Stock and Pink. All right, cool. Okay, so this is kind of like my wish list. What's the end game, right? So efficient is moving a lot of the focus of the community is on, but then robust and autonomous, I think, is the direction to go. Right? You want to be able to autonomously understand the data, and then at unprecedented scales and data rates. That's what's really different, right? So there's a lot of sort of on this continual learning area, robustness. There's a lot of research, but then doing this at unprecedented scales is really a co-design process with many axes, right? I think it's especially important on the robustness side, right? I mean, when you only get one crack at the data, it better be robust, right? Or you have a limited time. So this is different than like if you're just doing this online, you can put into ChatGPT 10 prompts until you get the right answer, right? You only get one chance to do it right. And then we heard lots of talks yesterday that are not really LHC related, but how you have these changing conditions in an experiment. How do you adapt to it? How do you calibrate? And so that's another interesting question. So along these lines, I started also. I'm just going to talk about interesting things that I find. This is a very personal view. Everyone probably in here has their own favorite sort of pet direction. The biggest one for me is like a lot of times in the community, robustness is completely at odds with efficiency, right? Robustness is just make it bigger, right? We'll find extra pathways and that's the way. Just build redundancy into your network, which is kind of like the exact opposite of efficiency. But there's lots of cool work coming out now. This is one. So Bobby, I was speaking at the workshop yesterday. How you can actually use compression to build more robust neural networks, right? So kind of compressing to the point where you can find let's say the essential latent information without like the model memorizing or something like that. That's a cool concept. And then this is Andy. Oh darn, I forgot to put the link for Andy's talk. So Andy gave a talk yesterday about fault tolerance in neural networks. And what's unique about this is really understanding faults at the bit level, right? And it's important for us in physics because you can have particles that go through your hardware, make single event upsets, and how do we understand that, right? And so this is a plot that I like to show. Let me walk through it for a second. So these are the total number of bits in the network and the empty histograms, and then the ones that we deem useful by the metric of it. Is it changing the final metric of the network? And for a small Pareto model, every bit is useful. For a medium one, most of them are useful, and for a big model, obviously less of the relative fraction of the model bits are useful. But the really interesting thing I like about this plot is actually if you sum up the bars for useful bits, the biggest network has the least number of sensitive bits, right? So it found the most optimal pathway by starting with a larger search space. And this is, you can imagine how this could be connected with sort of bit level pruning or understanding robustness or building sparse engines, things like that as well.
Sorry, this data comes for the quantized neural network, and what the piece of the quantization for this data?
So this one is 8-bit quantization, I think. So
Okay.
the x-axis is most
do you have
significant bits.
Have
Yeah,
you
from 0
explored the impact of the quantization in this data?
Yeah, so this is so sorry, this is only one axis of the cellular. This is just big and small, but for this particular data set, so I didn't give you any details on the data set. We can talk about it. There was already sort of an optimization on the quantization of the weights as a whole, right? So as well. Yeah, but yeah, for example, you could have that's a really interesting question, right? And, is pruning at the bit level give you more robustness, right? So some of do you need an 8-bit, a 9-bit, a 10-bit in the small case versus the large case? Does that? Yeah, it's an open research question for me.
So I guess like in this case, you can drop the lower 4 bits basically.
For large, yeah. So for large you could, right? For small you couldn't, right?
Yeah,
But let's say
yeah,
the
specific question comes from here. Does the quantized big neural network more robust than non-quantized small neural network?
Right. So this was just in terms of understanding. This is kind of the question of is it more robust is the next question. This is which bits are the most sensitive, and then we have to decide does it meet other robustness metrics. So this is kind of why I drew this thing here, right? We have to have metrics for us. This is some Pareto's optimal space, and usually we just draw it in these 2 dimensions, right? But now we have a 3rd dimension where we have to say, okay, it's performant, it's somewhere in the hardware, it fits the requirements, and is it robust too? That's a really interesting question. And here we haven't got to that step yet. FCARES is a tool to basically explore which bits are the most sensitive. That's how I would say it. Sorry, I didn't answer your question, I think.
That's good.
Okay, and then other work related to this is another complicated plot. I'll just kind of tell you the punchline, right? Is that okay? So now at the bit level, inspecting every single bit and saying is it important or not important is a computationally very very heavy job, right? You have to go through flip every bit. And so the question is, a priori, could you know which are the most important bits using something like gradients or Hessians? And it turns out, again, that if you use these sort of Hessian type of metrics, you can decide a priori without doing all of these fault injection campaigns. It's a pretty good correlation, at least for the most significant bits, which bits are most valuable. Okay, a couple more concepts and then I'll be done. So another interesting direction we can think about is lost landscape. So again, this is the next step. How do we, with one number, decide if a network is robust or not, right? And it can be thought of in terms of the landscape, right? Is it sharp and jaggedy? Are there lots of local minima? Is it shallow and broad, right? And understanding not just let's say the accuracy, but then the shape of the lost landscape can give you some idea of the robustness of a model. And so this is a paper from some collaborators at Berkeley, where they actually turned this into like a phase space diagram, right? So like, okay, this is the water phase, the gas phase, the solid phase of the neural network, and you want to be in this sweet spot that is both performant. Let's say, so this whole area is performant, right? But this is the most robust area, for example. So every model that you train is similar. You don't get a different answer if you get a different seed, things like that. Right? So, it's really interesting. You have these kind of weird, sharp boundaries in the phase space, for example, of like how wide the model is or the batch size, where it's like, it's not continuous. It's like something happened and the model is no longer robust, right? And so now we're starting to work with them on similar projects, but now thinking again about extreme quantization. So, here's like now scanning versus bit width and learning rate, right? Here's the bit width, right? And okay, so, maybe you would think, okay, so all 9-bit models are the same, but actually, this 9-bit model with this learning rate is much more stable than with that learning rate, right? The minima looks very different. And so, not all 9-bit models are built the same. They all have the same accuracy, right? But they have very different shapes of the loss landscape. Okay, I think that's it. This is purely speculative, but then I wanted to talk about like system co-design, right? You know, we talk a lot about edge, but there's this sort of really nice complementarity with, of course, also data center, right? You have something running on the edge, you have to be able to retrain it, know what's happening, re-update it, things like that. So some vision like this is for an accelerator complex, but I just stole the picture. This is actually one of those edge FPGA models running in the Fermilab complex right now. So this is just a monitoring tool that, yeah, but this is a big step for us. We're actually running AI on FPGAs for the control system of the accelerator, but just testing it out now. It's not doing all the work. And then this is the same thing, but at the LHC to create running that anomaly detection algorithm, right? So now you have this anomaly detection. It's you know, changing versus time. Why is it changing versus time? Should we be updating the model? Things like that. So, you know, the continual learning part of it. And there's a lot, I think there's still a lot to be learned about at the system level. How do you update the model? When is it time to update the model? Can you build that into your hardware? Do you need more bits? Do you need more transfer learning? What do you need? So, but this is kind of that toward that end vision. Okay, so I think I'm done. Here's a summary. I think it's exciting. It's an exciting set of problems to work on. They're also very hard, which I think makes you know, gives us a reason to sort of innovate. And I also think it's another reason it's exciting, but that may be unrelated. And I think the one thing that's come a lot, I mean, this journey over the past 3 or 4 years is also we build new types of collaborations with this, which is really cool. And so then I'm shamelessly stealing this. All right, cool. And then that's it. That's the last slide.
I have a bunch of questions. I was going to talk online. I just dropped it for the question. So first thing was a really cool talk. Thank you. What is the dimensionality of the data that you're dealing with?
Depends on which problem you're talking about.
Most of the problems that you're targeting with HLS for ML, are these two-dimensional, n-dimensional?
So I can give one example on your last slide, the anomaly detection.
Okay.
That's like 19 objects with 3 like momentum. So we have like 19 particle-like objects with like 3 momentum coordinates. So it's like 57, you know, dimensional space. That's our input, and we're trying to detect anomalies in this like 57 dimensional space.
And do you encode these 57 dimensions into a two-dimensional?
Yeah, so we encode it. Exactly, yeah. So we do use an autoencoder to reduce the dimension, and then I think it's 8.
It's an active exploration, the size of the latent dimension.
That's right, yeah. So that's something we can tune and change, but yeah.
You have pre-processing of dimensionality reduction, and then you do the ML to process the post-process data, right, on a much lower dimension, so the compute is on 8 dimensions, for example.
Well, no, the compute, this autoencoder like is the compute we're putting on this chip.
Okay, that's the first one, and then you do the anomaly detection probably.
Yes, yeah. Which in this case is basically just looking at like the way we evaluate this anomaly score is basically just in this like latent space, in this 8-dimensional space, just like a simple like mean squared error with, yeah, so.
But I mean, the applications are really broad, right? I mean, like there are, and this is maybe also the design challenge, right? Trying to satisfy lots of different, oh, sorry, I went too far. But let's say like, okay, yeah, so like this one, right? So like, these are usually RF spectra, right? These are like point clouds, kind of like what we were talking about, but the point clouds could be, you know, four objects with let's say 3 features, or it could be, you know, 1,000 objects with 7 features, right? So it depends on if you're doing clustering, if you're doing high-level objects, low-level objects, right? But then of course, the space that you need to do that would change as well, right? So for example, so many. All right, so like this is actually a good example, right? So let's say this project has basically 1 or 2 big algorithms, but then it'll be a lot like and it's taking in hundreds of particles, right? Or generating hundreds of particles, getting hundreds of inputs, and so it gets the whole board, right? And some of the things that like Javier is talking about, right? They're like little algorithms, and so they get like everyone gets a little piece of the pie, right? But you might be doing it for lots of different problems. So it's highly variable. And this is even just for the LHC, right? For different application, it can be very different.
Yeah, so any problem, any dimensionality, you're able to map it to a fully compute engine that's inside, and it still is efficient. So that's what precursor to my question was.
Yeah, yeah. The dimensionality of the compute engine, I think, is also the things that we're exploring. Like we have MLPs, CNNs, but there's also RNN research. There's transformer graph research as well, right? I didn't talk about the architectures.
The next question is, sad like this, it's a very stressful environment for the experiments, right? So you have a lot of single event upsets and radiation hazards. So
yeah,
you do redundant compute, and if you do redundant compute, how do you balance the latency?
Yeah. So I should say so this thing. Okay, so this thing is like off the detector, so it's okay. There's no radiation. But this chip that Giuseppe worked on, right, is immersed in a radiation environment, which is like 1,000 times what space is. So there, the chip, the first version of the chip has basically triple modular redundancy. And so actually the start of this FCARES study was originally to say which bits are, I mean, you can go to the talk, right, but which bits are the most valuable, and which are the ones that we should protect with TMR, and which ones are okay if, we'll just update them every second or something like that, even if they get flipped, right? So that was like the kind of way that we started. But then, of course, it's also interesting for like automotive and space applications as well.
Thank you.
But this doesn't damage the silicon, so it just flip it, right?
Yeah, it flips it, and yeah.
But it's not like you.
Yeah. Well, okay. Yeah, we're talking about transient upsets for this particular study, but there's also long-term damage as well that can happen, right, with the sensors. So that's a different problem that we also worry about.
Last question.
Do you have any multimodal problems where you fuse the data from different sensors?
Yeah, I mean, this is a multimodal problem, right? This well, it's the other end. All of these are I would say many of them are multimodal, right? Like this one is multimodal from different instruments, but I think, let's say, real-time critical multimodal is this one, right? I mean, this one is, we have 6 different subsystems, and they have very different detecting modes, and we have to combine them to make one decision, right? That is how it works like in autonomous vehicles too, right? I mean, you have, there's some like local, on that subsystem sort of decision making, and then they go past to some central thing that then makes a multimodal decision, right?
And for this fusion, do you still use the HLS for ML and QNX for quantizing those? Yeah. Okay. I would say the one thing that's maybe a little different is that there is still at the moment, we're working on one like very end-to-end problem, but it's generally each of the modalities, we try and interpret them in terms of physics objects that we're used to. Right, does that make sense? Yeah, we don't like just keep around latent spaces from all different sensors, and we just figure it out later. Although that is something I think we want to try. So it's still, each algorithm is interpretable in a physics way first, and then they're combined. Thank you.
So there is a question in the chat. What are the benefits of under 8-bit quantization for FPGA, considering that DSP typically doesn't support computations under 8 bits? Mm-hmm. And how does this impact the performance of an ML accelerator?
Yeah, I mean, this is something that Finn also sort of really tells her. We don't, we see this all the time. There was a cool talk yesterday about like scanning performance versus different bit widths, and it's fine. I mean, it's fine for us. We don't need to use DSPs, and sometimes algorithms share, right? So one will be DSP heavy, one will be LUT heavy. And it's a kind of a good complementary that we have this knob to turn as well.
From a logistic point of view, can we share the slides eventually? I know that this will be is recorded, so will be there. But if you Is it possible to put the slides as well?
Yeah, yeah, I just need to do
Yeah.
one thing that I forgot to do, which Jennifer did, which is get the get the material approved, but it should be fine.
That's
Yeah,
okay.
it's all public material anyways. I just need like one okay and then get a number and I can get it signed.
Are you doing some, your particular experiment, are you doing some repeat experiment? Or do you want to just one event? Do you experimented only one event, or are you doing the several events and then some average together? Or
So each event is statistically independent.
strictly independent?
Yeah, that's
So,
right.
but each event is supposed to be happen maybe a microsecond? Or
No, so each event happens every 25 nanoseconds. There's a collision. And actually, even in each collision, there are hundreds of or tens of collisions that we have to disentangle. Right, as well. But they're all
the
statistically-
collision, I'm talking about the collision. So you're talking collision, each event is a different experiment?
is a different, let's say,
In short,
image,
yes.
picture, right,
Yeah.
that you
In
take.
short, is yes.
Yeah, that's correct.
Each event is different, each collision is a different event, different condition or different event.
That's correct.
So I guess you trigger most of the events you wind up throwing out because they're not that interesting. So the trigger system is used to select the events that you want to keep and have interesting physics.
From the use, the select the interacting part.
What was it?
Interacting event. I mean,
Yeah.
I'm just curious.
So this particles decay really fast, so you take like a really quick picture, you have isolated like in time space, all the collisions. So you wouldn't have duplicating, I mean, there's some overlapping deposit, but not really.
It's like, yeah, you don't have an, oh, maybe that's what you're asking, like, you don't have an
Yeah.
exposure for like 1 microsecond and you collect all of them. It's just like, it's like boom, 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 every single time that there's a collision, you take a picture.
And so one event, but you take a photo, take the picture every some kind of second.
Yeah.
Every 25 nanoseconds, it's like a heartbeat, every detector is sort of operated at that speed.
So if I give a context, I think for the Higgs boson thingy is 1 every 1 billion, you're going to detect something that is used for the experiment, right?
Yeah, so like exactly, so the collaboration is built up of, okay, other people are searching for other things too.
Yeah.
So- But let's say the Higgs team, right, there's like, dozens of people, and they're looking for this one thing that happens once every billion times. But actually, the Higgs then decays into like 6 different ways, and then some of them only happen a few % of the time, and then we're looking for very specific. So it's really down here. This is like just the entry point.
And
But
then,
most people look for stuff like down here.
and then what happens is to have a significance, you have to take millions of those. So think about it, you take 1 in a billion for your experiment, and then you have to take 1 million of those just to have a 3 sigma kind of description. So every single a compat is an event, but it can be used for different purpose.
It's like, yeah, it's just a probabilistic. Sort of
I mean,
distribution.
so do you need some kind of near time, almost, yeah, not the, almost near time, so you data processing.
Yes.
Yeah, so the real-time processing is mostly to do data reduction for us.
For
Yeah. But other problems in science,
because of the unit of the data reduction.
it's too much data, yeah, so that's the kind of the point, right? This is petabits per second.
Yeah,
10
per
petabits
second.
second, which is completely untenable to keep.
I mean, so your sampling frequency is 40 megahertz.
Yeah,
Yeah,
exactly.
so there's a one event happen, and then your 40 megahertz sampling rate, you just collect the data.
Right.
And then for that purpose, you need the data reduction and then you use the.
Right, and this is basically up to here, sorry. This is the real-time stack, right? And then and then you save the data. But this is like yeah, sampling rate of 40 megahertz for a billion pixel camera, but it's the billion pixel camera is split into lots of different modalities.
And then the camera, probably, do you have each photo, do you use photo diode? Or each photo diode have the different response time to check the. You're using the camera for detect the signal?
Response time?
Yeah, response time.
Oh, it depends on the subdetector. But somewhere between, let's say, well, some people are thinking about 100 picosecond detectors, but let's say hundreds of picoseconds to, let's say, tens of nanoseconds.
Okay.
Right? Depends on the technology of detection, because it's not really a camera. camera is just an analogy we use, but there are all kinds of sort of.
I mean, the inside of the camera, there's supposed to be a detector, photo detector, and then each photo detector has the dispense time, and the dispense time is also dependent, rely on the semiconductor, some kind of.
Yeah. If you have that
time, there's some
demonstration
related.
Oh, yeah.
If you like,
Like this
yeah,
one.
like, yeah, exactly. So like the response time we're talking about is like how wide these pulses are, basically.
Yeah, and it depends, right? So like for the fusion experiment, right, this pulse is 3 microseconds. For a tracking detector, it's 1 nanosecond.
Yeah, one,
Right,
yeah,
yeah.
usually the probably around 1
Yeah.
usual time. Yeah,
But they're designed that way because you know that the experiment has to take a picture every 25 nanoseconds.
Yeah.
Right.
Thank you. I stop recording.
Okay, yeah. I'm afraid if I